Everything okay? Hello.
Hello.
My screen visible, audibility. Hello.
Yes, sir, it's fine.
Okay, fine. So, so let me start. Okay. So last lecture we looked at linear transformations from one vector space to another, and looked at given ordered basis how to represent a linear transformation in the matrix form. Then we looked at notion of perpendicularity for vectors and how that gives rise to notion of orthonormal basis for the vector spaces. So where the notion of angle comes from the dot product in Rn. Okay. So today we are going to look at linear transformations on vector space to another, but we are with respect to ordered orthonormal basis. So we'll start looking at that and see how what difference does it make. So let us start by looking at linear transformations V to V, and if you recall, when we started looking at linear transformations on vector spaces, we wanted to look at those maps which preserve collinearity and division ratios. And now, because there is an additional uh, structure, namely the angle available, which we dot product, which we denote by this bracket, we will say that a linear transformation is an isometry if the inner product or the dot product of V with the TW is same as the dot product of V with W. That means if you take two vectors V and W and take their images TV and TW, then the dot product between the images and the original vectors is same. So then such a thing is called an isometry. So you can think of isometry as a map which preserves angles. Okay. So here is a very small simple theorem which is very useful because dot product is related with the length of the vectors. A dot A is equal to the magnitude square or the norm square. So these two are not easy to not difficult to see that saying that T is an isometry, it preserves angles is equivalent to saying it preserves distances. Both are equivalent statements. So if it preserves angles, it will also preserve distances. And if it preserves distances, then it also will preserve angles. If you want a formal proof of that, that is quite easy. The norm of TV is equal to the dot product of TV with itself, and that is equal to dot product of V with itself. So 1 implies 2 is obvious, and 2 implies 1 is also obvious if you look at the dot product of T of U plus V. So let us just so look at the dot product of T of U plus V and expand it using the properties of the dot product, linearity and distributive property. So that gives you this. And also on the other hand, if you look at because it is an isometry, so you have got this is also equal to the dot product of U plus V with itself. So expand that, and one or two comparison gives you that if the distances are equal, then the angles are also equal. So an isometry is a special linear transformation from one vector space in Rn to another, which preserves angles and equivalently preserves distances. Right. Now let us also observe one thing that if T is a linear transformation and we have a ordered orthonormal basis V1, V2, Vn, then the matrix representation of T with respect to B T is from V to V. So we are taking the same orthonormal basis V, okay, on both domain and the range. Then its matrix representation is immediate and is given by TV. The first column, if you like, is TV1, V1, TV1 with V2, dot product with Vn, and so on. That is obvious because we said that the coordinates of a vector are immediately known if you have an orthonormal basis. The dot product gives you the coordinates. Right. So with that knowledge, this is obvious that this is the matrix representation. So that is a additional kind of information. In case we have a ordered orthonormal basis, we can write down immediately the matrix representation in terms of the dot products. Okay. And now, if I look at the dot product of one column with another, okay, then what it looks like. So if I look at the dot product of this column with this, then it is just equal to T of Vj Vk. So if you look at dot product of jth column with kth column, then dot product this into this plus so on. So that is just Tv Vj. And if T is an isometry in addition, then this will be equal to the dot product of Vj with Vk. And that being a ordered orthonormal basis will be either 0 or 1 depending on j is equal to k or not. So that immediately says that if T is an isometry and B is an ordered orthonormal basis, then the matrix of T has a special property. Are uh, its columns are orthogonal to each other. Okay? And it's not difficult to see why is that is happening. And if you write A transpose A, if A is in terms of the column representation, these are the columns of A, then A transpose A can be written as the dot product of the columns. So this also gives you that if T is an isometry, then A transpose A is equal to identity. So isometry if and only if the columns form a right? And if only rows also form, because A transpose A, you can take the transpose of that, that also will be uh, perpendicular to each other. So for an isometry, the rows and the columns form orthonormal sets. Uh, in terms of matrices, we can write this as that A transpose A is equal to identity, and such matrices are called orthogonal matrices. So that gives rise to a new type of matrices called orthogonal matrices. Orthogonal matrices are the matrices of linear transformations which are also isometric. So this is uh, what we get. You can write A is orthogonal, A transpose A is identity, uh, A transpose is equal to identity. And any one of them is satisfied for the matrix of the matrix of the linear transformation. That matrix is an isometry. So an isometry which is a linear map that preserves angles, equivalently preserves distances, and gives rise to, in the matrix form, what are called orthogonal matrices. Right. So, so orthogonal matrices arise in the matrix representations of isometries with respect to, of course, orthonormal basis. Let us look at some examples. Let us look at a map from T from R to R as a linear map. So the only linear maps are Tx equal to alpha times x, where alpha is fixed. So this is if this is to be an isometry, obviously we should have the mod of right. If this is to be an isometry, then the mod of alpha should be equal to 1. So the linear map Tx is equal to alpha x is an isometry in R to R, provided mod alpha is equal to 1, if and only if. So this gives a description of all isometries from R to R. Let us look at another case. Let us look at example of R2 to R2 in the plane. The transformation is given by Txy is equal to x cos theta plus y sin theta minus x sin theta y cos theta. Okay, so T of a point xy is x times cos theta y sin theta, right? So a matrix representation of this, if you want to write, one can write, but let us first observe that this is an isometry. So norm of Tx square will be norm of Tx square we can compute. Now this square plus this square root. So that comes out to be x square. So T is an isometry. Okay. So the question is, what are all isometries of R2? Okay. Can we characterize all isometries of R2? And there is a theorem which one can prove very easily, that if T is a linear map and the matrix of T with respect to the orthonormal basis, you can take the standard orthonormal basis if you like. Okay, and then its matrix representation, it will be an isometry if and only if its matrix representation is either cos theta sin theta minus cos theta, or cos theta sin theta minus sin theta cos theta. It's not very difficult to prove this theorem. Let me just probably give you a hint how to prove it. You can do it yourself later on. If T is an isometry, if T from R2 to R2 is isometry, and let us say the matrix of T looks like, say, A, B, C, and D, right? So if it looks like A, B, C, D, uh, then these columns are orthogonal. So what does that mean? If the columns are orthogonal, that means A, B, rows and columns both you can look at, and then the rows of A are orthogonal, rows of B are orthogonal. That gives you uh, uh, and orthonormal, actually. The form C transpose is identity. So I will give you A square plus C square is equal to 1, B square plus D square is equal to 1, and A square plus B square equal to 1, norms equal to 1, C square plus D square equal to 1. So all the norms are equal to 1, and perpendicularity will give you AB, uh, AB plus CD, AB plus CD is equal to 0, and AC plus BD equal to 0. So you have got so much of data available to characterize AB and CD. One can actually from here, one can, because a square a b c d, a square plus c square is equal to 1. So from here it's easy to see that absolute values of a is less than or equal to 1, and b and so on. So you can take a to be equal to sine theta and c equal to cos theta, and then compute everything from this. Okay, so from here you try to take a equal to, say a is equal to cos theta, then b will be a square plus b square equal to sine theta, and so on, and make computations. So you'll get the required result, namely the only possibilities are that cos theta minus cos theta sin theta minus sin theta cos theta, where theta is an angle between 0 to 2 pi. So this gives you all the isometries of R2. Okay, and you can see that one of them is the rotation. Okay, and the other is a reflection by an angle theta. Rotation and reflections, and of course their combinations will give you uh, other isometries also. So these are all isometries of R2. Uh, the question comes, can we sort of go over and try to find all isometries of R3? And that is also possible, and that is a very instructive construction. So let us make a assumption that T is a linear map, okay, R3 to R3, and let us assume that it has a special property that there is a vector u, a unit vector of length 1 with a property that tu is equal to lambda u for some lambda. Okay, such a lambda we will see later on is called an eigenvalue, and this u is called an eigenvector for this. And this assumption actually is always satisfied in R3, so we'll prove that also later on. For the time being, let us assume that such a property is true for T. In that case, if you look at T as a isometry and with an eigenvalue lambda and u as a unit vector, then the following are true, that absolute value of lambda is equal to 1. One can show that. The space R3, if you look at the space generated by this u is the unit vector, then R3 splits into direct sum W perpendicular, right? So W is one dimensional space and orthogonal complement of that is W perpendicular. So you can write split R3 into two parts, and that actually also implies, because U is an eigenvector for eigenvalue lambda, W is actually invariant under T. That means if you take a point in, obviously, because if you take alpha times u, then T of alpha times 2 is alpha times T of u. That will again be a scalar multiple of alpha. So that again will be a uh, eigenvector. So that says that this is a invariant subspace, and perpendicular also is an invariant subspace. So essentially that means you can restrict T to W, that is one dimensional, and T to W3, which is W perpendicular, which is two dimensional, and will be which is also invariant. And on one dimension we know what T looks like, so these are invariant subspaces of T. Once that is obtained, once that is proved, one can restrict T to W. It is one-dimensional isometry that we know how does it look like, and two-dimensional isometries we don't know how those look like. So we can decompose T into two parts, that on W elements of the type alpha times u, what it looks like, and what it looks like on W perpendicular. So that will give us all isometries of R3. The main thing is that existence of an eigenvalue with the property that there is a vector u such that Tu equal to lambda u. That helps us uh, to decompose R3 into two parts and analyze on each part separately. So one can now write down that the isometry T will be on W. Either it will be Tu equal to u. U is that orthogonal, that is the eigenvector, and on W perpendicular, it can be a rotation, or it is Tu equal to u identity on W, and on W perpendicular, it is a reflection. So identity, rotation, identity, reflection. Here it is reflection in the one-dimensional space, and here it is a rotation in W perpendicular, and a reflection, and then again a reflection in W perpendicular. So there are four possibilities for T to be an isometry. W, it looks like either of this, and on W perpendicular, it looks like this. So main one, it is very satisfying to know this method of analyzing the isometries on R3 gives us complete description of isometries. Okay, and the tool which helped us to do that was that we found a subspace W of R3 which is invariant, and W perpendicular also to be invariant. So we could restrict to the two parts separately and analyze them. And this is basically a prototype of what is going to come eventually, all the sort of theorems later on for writing various standard forms or various forms of matrices. So we'll see that. Okay. So what use was helpful was an eigenvalue. So let us define this concept that a scalar lambda is called an eigenvalue if there is a vector x, non-zero vector x, say that ax is equal to lambda x. And this vector x is called an eigenvector for the eigenvalue lambda. Right now, of course, obviously the problem we would like to analyze it. We assumed for R3, given a linear transformation, there is a eigenvalue. Okay, so in general, the question is, given a matrix A, find its eigenvalues, and corresponding to each eigenvalue, find out eigenvectors. Okay, so lambda is eigenvalues. The scalars x is ax is equal to lambda x. That is the eigenvector for the eigenvalue lambda. So to understand this problem, let us just write that eigenvalue a, uh, right? Saying that v is an eigenvector for eigenvalue lambda is the same thing as saying that a minus lambda I applied to v uh, is equal to 0, and v is a non-zero thing, right? Written this way, obviously it says that we have got a non-zero solution for the homogeneous system a minus lambda I applied to v equal to 0. So now let us go back to system of linear equations. When does a homogeneous system have a non-zero solution? For a matrix applied, right, for this matrix to V, this will have a non-zero solution only when this matrix A is not invertible, because if it is invertible, I can apply A inverse, this inverse, and I'll get V equal to 0. So for the homogeneous system, Ax is equal to 0. Uh, uh, a non-trivial solution exists only when the rank is less or the matrix A is not invertible. So saying this matrix is not invertible, we can go in and write it this in terms of determinants. Now we have not discussed determinants here, but I think most of you are familiar with the property that a matrix A is invertible if and only if its determinant is not equal to 0. In fact, it's very one the topic of determinants is itself quite nice, and you should read in detail about determinants, because we only in our courses normally we do only the computational aspect of determinants. Determinants have certain properties, and we give a matrix and compute determinants and so on. We never bother to ask questions like a determinant actually is a function on matrices. For every matrix, square matrix n cross n, you can associate a number called determinant with certain properties. What are those properties? Do we require all the properties to define it, or is a minimal set of properties which are good enough to define and deduce all other properties from it? Okay? And whether such a function exists and whether such a function is unique. So, what is determinant function? Does it exist? Is it unique? All these questions at some stage in your study of linear algebra, you should ask and try to get familiarized with. Anyway, for the time being, because we don't have time to go through all those concepts, we'll assume you know determinants, and you know how to expand a determinant either by a row or by a column, and the property that the matrix A is not invertible if and only if its determinant is equal to 0. So for we apply that here. If this applied to V is a homogeneous system, has a non-trivial solution, that means A minus lambda I is not invertible, so its determinant must be equal to 0. So and that means that so that is the determinant of A minus, if A is A11, A12, A1n. So A minus lambda I will be this n by n determinant, right? You can call it as d lambda or d lower suffix a lambda, right? To indicate it is with for the matrix A, and so this is called determinant of A minus lambda I. Lambda will be a parameter which we don't know actually. Okay, so it will be a polynomial in lambda. So determinant, or this is also called the characteristic polynomial for the matrix A. So for a given a matrix A, its characteristic polynomial is determinant A minus determinant of A minus lambda I, which like this. If you expand it, you can actually see that this will it is a polynomial of degree n in lambda, because lambda is appearing in each row. If you expand, and so cross these terms will give you a term which will be degree n lambda, and the coefficient of highest degree will be minus 1 to the power n. So it will be minus 1 to the power n lambda n and plus so on. So it will be a polynomial, and that polynomial is called the characteristic polynomial. So eigenvalues of a matrix are the roots of this polynomial. So that is what we are. So the possible roots, because we know that if we treat if the coefficients are real, then the characteristic polynomial may not have a real root, but it will always have complex roots because of the fundamental theorem of algebra. So treated as complex over the field of complex numbers, it will have n roots, and those roots may be repeated. So that is called the multiplicity of the root. Right. So let us go over a bit more, because I will skip examples for the time being, because what I want to say. Okay. Uh, so here are if uh, this is about the determinants using determinant properties. If A is similar to B, what is meaning of A similar to B? There is an invertible matrix, say that P inverse is equal to B. Then you say A is similar to B. So similarity is A is similar to B if there is a matrix P invertible, say that P inverse is equal to B. That is called we say A and B are similar, and we write it with the symbol similarity. And it's quite clear that if A and B are similar, then the characteristic polynomial, here we have called as g of A, is it will have the same roots as g of B. They are also okay. Here, for given a polynomial g, you can look at g of A. That means substitute the variable by A, then A will be similar to g of B, and that will also imply that uh, the roots of the characteristic roots of GA are equal to that polynomial. Okay, it will be polynomial substituted there, and GA, the polynomial GA is also similar. This is similarity of matrices. If A is similar to B, then the polynomial equation in the matrix A is also similar to the polynomial equation in B. And once two things are similar, they will have the same characteristic polynomial and same roots, right? Because of determinant AB is equal to determinant A into determinant B. So if A is similar to B, then the characteristic polynomial of A is same as characteristic polynomial of B. And so characteristic polynomial of GA will also be characteristic polynomial of GB, right? So these will use it slightly later. So let's just comment that. So how do you find the how do you find the eigenvalues? Look at the characteristic polynomial, find its roots. That is a problem. And given for each eigenvalue, to find the eigenvector, we have to solve that equation A. So let me just write here. So determinant of A minus lambda I equal to 0 gives eigenvalues and a minus lambda I for each such u equal to 0 gives eigenvector for lambda. So this is solving a homogeneous system. Again, you will have to go to your row equivalent forms to find out. This is solving a given a polynomial, how to find roots of the polynomial. So that is the work involved. And in this second thing, the work involved will be uh, finding solutions. So for a homogeneous system, find out all possible solutions. So that is the work involved. Right. So, so if lambda is real characteristic root, then we write E lambda because we were looking at only the real matrices. The null space of A minus lambda I, right? That is that is the set of all vectors which are possibly eigenvectors, right? Of course, 0 is not an eigenvector, but we can add that to that set and call that as the null space of that matrix A. Okay, and lambda is complex, and the eigenvector will also be possibly complex. Okay, and obviously, because we're looking at the roots of a polynomial, if A is if we're in R3, then the linear transformation T from R3 to R3, okay, will its characteristic polynomial will be a polynomial of degree 3, which is odd, so we'll have a real root anyway. Okay, so that is what we had assumed in our considerations when we looked at isometries of R3. Okay, so we can look at matrices and look at eigenvalues and uh, try to find out uh, when are the eigenvectors uh, linearly independent. In that subspace, we can find out the basis of the null space and so on. Okay, so here is uh, let us start proving. Forget about this slide. Let us look at A be n cross n real matrix and lambda be an eigenvalue of A. So E lambda is looking at all the vectors U, okay, such that F is the real line here, AU equal to lambda U. Now it is a subspace, okay. It is a subspace of n because given two eigenvectors u1 and u2, a u1 is equal to lambda u1, a u2 equal to lambda u2. So a of u1 plus u2 is also is equal to lambda of u1 plus u2. So it forms a subspace, and of course alpha times eigenvector also is an eigenvector. Okay, if alpha is not 0, so we can add 0 to it and form a subspace called the eigen subspace of the corresponding eigenvalue. So here is an important result which says if lambda 1 lambda 2 are distinct eigenvalues of A, if the eigenvalues are distinct, okay, any collection of them, okay, lambda 1 lambda r, and v1 v2 vk are eigenvectors corresponding to these eigenvalues, then they form a linearly independent set. So we'll prove that. That is an important result. And finally, so for each eigenvalue we can look at if lambda 1 lambda 2 are distinct eigenvalues of A, and for each eigen subspace lambda I, we can form a basis of that eigen subspace and put them together into a box. So that gives you a set of linearly independent eigenvectors. Okay, B1 eigenvectors, a basis for the eigen subspace of E lambda 1, for E lambda 2 and E lambda 3. Each one of them are themselves independent because they are basis elements. And B1, B2, they are independent because they are distinct because of 2. So this is a linearly independent subset of Fn and consists of eigenvectors. Okay, how many are there? That is going to be the real problem later on. So let us write that for lambda 1 to lambda r, distinct eigenvalues, the dimension of the eigen subspace be equal to mi. Okay, so this eigen subspace, its dimension, that is a null space A minus lambda I, dimension be equal to mi. Yeah, so in that case, we will say that, or we will prove that, or it is easy to prove, obviously, obvious thing, that um, A is diagonalizable. What does that mean? We'll look at that. What does diagonalizability of A mean? So we'll explain these things one by one. Okay, right. So let us look at problem number 2, namely, one is obviously we have seen it is a subspace. So let us skip that. So let us look at, we have got k distinct eigenvalues. Let us choose any L less than or equal to k, be the smallest integer, such that v1, v2, vl is linearly dependent. Keep in mind. So the first time v1 itself is independent, maybe v1, v2 is independent, and so on. But first time when you add VL, it becomes dependent. So that is the smallest integer that becomes dependent. Because this set is linearly dependent and V1, V2, VL minus 1 is independent. So VL must be a linear combination of the previous ones. So VL is a linear combination of the previous V1, V2, VL minus 1, because this is the smallest so that it is independent. So let us now apply A to it both sides. So when you apply A to both sides, you get this equation. So lambda L, AVL is lambda VL, and being a sum, I can distribute it linear transformation. So it is equal to this. Okay. Also, from the equation lambda VL was a linear combination, so I can multiply by lambda L on both sides. So I get this. So subtract, we get it equal to 0. And once it is equal to 0, I should have V1, V2, VL minus 1 are linearly independent. So that should give you that the coefficients all are 0. Okay, all 0 for all I. But that is not possible because they are all distinct. Okay, alpha i's are not 0. Since alpha is not 0, so one of them would be 0, and that is not possible because the eigenvalues are assumed to be distinct. So that means that L, which is the smallest dependent, is actually equal to n. So all are linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. One proves it. Okay. Oh, there is a problem in the typesetting. So collect together the linearly independent elements for each eigenvalue. So ignore this and you just think of this as the collection of eigenvectors corresponding to, and you can uh, prove that this union of that collection is also independent. So I think let me leave that as an exercise for. So as the part 3, I'm slightly fast today because I want to reach a target. So what I'm saying is this following thing, that B1 is a linearly independent set, a basis for the eigen subspace lambda 1, B2 for lambda 2, Br for lambda r. If you take the union of all of them, then that is a linearly independent set. Okay, right. So that is what we are saying. So again, example for the time being. So I'm already slightly behind time. What I want to do. Okay, so let us look at this concept. Lambda is a root of the characteristic polynomial. So that is called the algebraic multiplicity. The root may be repeated. So that is called the algebraic multiplicity of the eigenvalue. Okay, so m lambda is the algebraic multiplicity of A, and we call the dimension of the null space is known as the geometric multiplicity. See, dimension of the null space for a eigenvalue lambda I, you are looking at the eigen subspace and looking at its dimension. Okay, that may not be as much as the order of the root lambda I for the eigenvalue. Okay, so it will be always be less than or equal to that. So that is what is called the defect, that the difference between the algebraic multiplicity and the geometric multiplicity is the what do we call as a defect for what. I will just now illustrate that. Supposing they were equal, then we would have gotten a basis for the underlying space Rn, which will be consisting of a chunk of eigenvectors for the eigenvalue lambda 1, a chunk of eigenvectors for lambda 2, and a chunk of eigenvectors for lambda r, and they are all distinct, right? So we'll have a basis consisting of eigenvectors for the underlying field Rn, underlying space Rn. So that is what is going to be important. So let us algebraic multiplicity and so okay, let us probably skip all this. And the question we want to analyze is the following: given a matrix A, when does there exist a invertible matrix P? Say that P inverse AP will be a diagonal matrix. Okay, so that is a question we would like to answer, because see why one is interested in this kind of questions is the following: because uh, P inverse AP, when you multiply a matrix A by P, okay, it is essentially where P is invertible and you are changing a basis. Actually, essentially it is a change of basis. So what we are trying to do is, given a matrix A, okay, can we have a different basis for the underlying space, so that with respect to that basis the matrix A looks like diagonal, because diagonal matrices are very simple. So that is what is essentially called also the, this is also called the diagonalizability problem. So if such a thing is possible, we say that matrix A is diagonalizable. Right. So let us, that is what is saying diagonalizable if that kind of a thing. If A is similar to a diagonal matrix. So this question, let us just try to answer this question naively. Says if lambda 1, lambda 2 are, if A is diagonalizable, if and only if there exist n scalars, okay, we are not saying all distinct, and vectors C1, C2, Cn, say that ACi is equal to lambda I Ci. So that means A has got n eigenvalues, and C1, C2 are linearly independent, and hence form a basis of it, right? So if these two conditions are satisfied, then the matrix is diagonalizable, and conversely. So let us just look at that. So given C1, C2, Cn, form a matrix P, which are the columns with columns as the C1, C2, Cn, because they are linearly independent. So the rank of this matrix will be full. So P is invertible, okay, and none of them is obviously 0, and is a full rank. And if you multiply, uh, if you write D as the diagonal elements lambda 1, lambda 2, and 0, then P inverse AP applied to D implies AP is equal to PD, and that means I can take it on the other side. So AC in the columns form, it is equal to this, and that says that ACI is equal to lambda CI. So if that is diagonalizable, okay, then CIs are the eigenvectors and lambda I are the eigenvalues. Conversely, suppose there are elements such that they are the eigenvectors for eigenvalues. So there are n eigenvalues, and each has got a eigenvector. So right. So if this is the case, then we'll form the matrix P with these eigenvectors as the columns, and once that is done, we can easily check once again that AP is equal to PD. So that is diagonalizable. So basically what I am saying is that to say a matrix is diagonalizable, we should be able to get uh, n eigenvalues and n eigenvectors corresponding to them forming a basis, n linearly independent eigenvectors. Then the matrix becomes diagonalizable. Okay, so they will form a basis of Vn. So when is that possible? That we have already actually seen. I think this is a repetition of that. So let us skip the repetition. So let us assume that the matrix is such that all eigenvalues are distinct. Okay, so A is a n cross n matrix, and all eigenvalues are distinct. If all eigenvalues are distinct, just now we proved that the eigenvectors corresponding to distinct eigenvalues are linearly independent, right? So there will be a basis consisting of eigenvectors if the matrix A has got n distinct eigenvalues, and that will be diagonalizable. Okay. Uh, So let us, that is a very nice case and very rare case that you will have. So we have the algebraic multiplicity, geometric multiplicity, and that is the defect. And let us look at. So if the algebraic multiplicity agree, then obviously we'll have a basis consisting of eigenvectors, and the matrix will be diagonalizable. Okay. I've been slightly fast because we have only one hour to. Uh, okay, so here is this is an example. So here is an important class of matrices for which this is possible. So what we are saying is, if A is a real symmetric matrix, so what is a real symmetric matrix? A is equal to A transpose. Then A has n real eigenvalues with real eigenvectors. So it will have n eigenvalues, and it will have n eigenvectors which are linearly, it will have n eigenvalues and n eigenvectors. So let us see what it means, why it is so. Uh, So first of all, even if it is a real matrix, as a characteristic polynomial of it will have n roots, but they may be complex. So let us say z is a root of the characteristic polynomial for and for the characteristic polynomial lambda is a root, and u is an eigenvector for it. So to show that lambda is actually real, one can easily prove it. Look at u transpose. If au equal to lambda u, then that gives you uh, that is a dot product. Okay, so look at the dot product of ax with y in Rn. We know this is given by, you can take it on the other side. So lambda norm u square is equal to, and this lambda you can take it inside here, and it is au. Okay, and that on the other component goes as a transpose. So a transpose u, but a and a transpose have got the same eigenvalues, so this is also equal to lambda. But when you take it out in the complex inner product, complex dot product of complex quantities, this comes out as a lambda bar. So lambda bar of u square. So because u is norm 1, so or u is not 0, So lambda is equal to lambda bar. So that is a real eigenvalue. So eigenvalues of all real symmetric matrices are actually real. Okay. So and because as a complex characteristic polynomial has n roots, so all roots are real. So all eigenvalues of a real symmetric matrix are real. And the second thing that one proves is the following, namely that the eigenvectors corresponding to distinct eigenvalues have a special property, and that says that if lambda 1, lambda 2, lambda k are distinct eigenvalues, right, then the eigenvectors corresponding to them not only are linearly independent, okay, to distinct eigenvalues, actually they are orthogonal. So that can be proved. Okay. It's not a very difficult thing. Probably we can just look at once again. So lambda I ui uj, ui is eigenvector for lambda I and uj for lambda j. Then we can just write that as in terms of a and shift it to a transpose. That becomes uh, lambda of lambda j uj. So ui uj is equal to, and because they are distinct, so it will come out, right? A transpose is real symmetric, so A transpose is equal to A, and that is equal to lambda j. So lambda j comes out. So lambda I of ui uj is equal to lambda j of ui uj, and because these eigenvalues, these are eigenvectors for the eigenvalues lambda I, lambda j, they are distinct. Lambda I is not equal to lambda j, so this is possible only when ui uj dot product is equal to 0. So eigenvectors corresponding to distinct eigenvalues in a real symmetric matrix are orthogonal to each other. Okay, right. So here is uh, n real eigenvalues with it. Okay, this why it is. I think my slides are slightly repetitive today, so let me just skip that. We have already proved it. Is an orthogonal set. So that we have proved just now. So we proved this just now. Okay. So let so lambda 1, lambda 2 are distinct eigenvalues, and the eigenvectors corresponding to the eigenvectors, they form a orthogonal set. And then the claim is that there actually exists a orthogonal matrix P such that the following holds, that P inverse AP is equal to diagonal. The diagonal entries are the eigenvalues. N eigenvalues were there, so the column vectors of P are the eigenvectors for the corresponding eigenvectors. I'm skipping the proof of this theorem. Actually, one can proof is not very difficult, but it is an inductive kind of a thing. So I think at some stage in your classes in linear algebra, you will come across what is called the spectral theorem for real symmetric matrices, or called the diagonalization theorem for real symmetric matrices. So the basic idea is that for a real symmetric matrix, uh, there are as many eigenvalues as the dimension, and the eigenvectors corresponding to distinct eigenvalues are orthogonal to each other, and the algebraic multiplicities are equal to the geometric multiplicities, so it becomes diagonalizable. This is an example. Uh, Dilpreet, how much time I can take? 5 minutes more? Okay, there is no. No, I'm just asking. Hello. So this is an example. Okay, probably I think let me just probably say something more, and probably we can look at the examples later on, because this involves quite a bit actually. So let me just so if you have got a matrix like this, 0, 2, 2 and 0, 2, 2. So that is a real symmetric matrix. Finding eigenvalues means finding the roots of the polynomial. So that is a cubic, and you find that lambda equal to 2, minus 2 and minus 2. So minus 2 is a repeated root and algebraic multiplicity 2, and lambda is equal to 4 is also an eigenvalue. For these eigenvalues, when you want to find out now the eigenvectors, you will have to solve a minus lambda I. Okay, look at a minus lambda I, make it to reduced row echelon form, and find out how many pivots it has got. So it has got only one pivot, so independent number of independent variables will be equal to 2, so it will have two linearly independent eigenvectors for the eigenvalue, and that can be found out by giving the variables value 0 and 1, 1 and 0 for the those who are dependent variables. So here pivotal variable is the first one, so you can give value this variable 0 and this 1, and then you compute this, and the next time give this value 0 and that value as 1 and compute, so you'll get two linearly independent eigenvectors. Or it says that uh, eigensubspace is described by this, so this equation, so you can give x3 equal to 1, okay, and x2 equal to 0, you'll get x1 and you'll get two eigenvectors. Okay. Similarly, for the other eigenvalue lambda equal to 4, you find out its actually multiplicity is algebraic multiplicity is 1, geometric multiplicity also is 1 because the rank is equal to 2 for a minus lambda I. So you find basis uh, for the eigenvectors, okay, but they may not be perpendicular. So you got a basis which is linearly independent. You have to apply Gram-Schmidt process to orthonormalize it to make them perpendicular. Okay, so that will give you a matrix that will give you a basis consisting of. So this is the Gram-Schmidt process applied. You'll get x1, x2, x3 tilde as mutually orthogonal. So this is the mutually orthogonal set of vectors which are eigenvectors for the first two for the eigenvalue um, lambda equal to 2, and the second one for 4. And when you write P as the matrix with this as the columns, that will give you P inverse AP to be the diagonal. So that is what diagonalizability of a real symmetric matrix is involved. Okay. Advantage of having diagonalizability is, for example, you want to write e raised power xa, okay, for a matrix A. This can be simply written as by if you want to write this, that is if it is diagonalizable, okay, P inverse AP is diagonal, then it is P times this, and that is simply the function goes up in that, so e raised power xd, okay, is this, so where e raised power xd is this. So that is the advantage of diagonalizability. It helps you to compute things very easily. Another application of diagonalizability is what is called quadratic curves. For example, an equation like in two variables ax square plus 2bx plus cy square plus this, right, is a quadratic equation in two variables. This is called a quadratic curve. Um, and if you can make these coefficients of bxy dx and dy to be 0, then it is called the standard form. And that standard forms are, for example, a circle, ellipse, hyperbola, parabola are all standard forms of the quadratic curves. So to do that, one applies one can apply the diagonalizability, right? Making in this form, one has only shift of origin is required, so that can be done. Once that is done, you write a quadratic form like that, and for this quadratic form you can easily write down so basically diagonalization of matrices help you to recognize what is the quadratic curve. Okay, so I'm again rushing through very fast, so that is one application of it. I just want to conclude this with an application of diagonalizability, which normally is not in the books. So probably let me say that. What is it? So that is what is called Kelly-Hamilton theorem. Kelly-Hamilton theorem says that every square matrix satisfies its characteristic polynomial. So what does that mean? So I mean, if FA T is the characteristic polynomial, what is it equal to? That is equal to determinant A minus determinant of Ti minus A if the variable is T. And uh, one can naively say if I replace T by A, then it is A minus A, it is equal to 0. That is not what we are looking at. F A of T is a polynomial in T, right? We saw that. So if you place T by A in that polynomial, then that equation is satisfied. Okay. For a diagonal matrix, it is obvious that it is satisfied. If A is diagonalizable, then also it is satisfied because for under similarity, the characteristic polynomials don't change. So that is advantage of diagonalizability. That if you can make a matrix diagonalizable, then for the diagonal matrix, Kelly-Hamilton theorem is true. And the main crux of the proof lies in the fact that diagonalizable matrices are dense in all complex square matrices. This is something denseness coming from metric spaces or topology. Normally, books in algebra don't sort of talk about these things. Proof of Kelly-Hamilton theorem is normally given via determinants, and pure algebraic proof is given. And here is a proof which I'll just outline this proof quickly so that you can try to understand it later on. So for any matrix, this is the first thing, that any matrix with complex entries can be uh, made similar to a upper triangular matrix. So that means along the diagonal, the entries are there. There are some diagonals above, and below everything is 0. So this is a result which can be proved for complex matrices. That means A can be made similar to B, whether B is upper triangular. So that is one result. We are not proved that, but can be. It's not very difficult to go through the proof of that. So that is step one in the proof, and the step two is, now what we do is we modify each one of the entries, okay, in this B by slightly. So lambda 1 plus epsilon, lambda 2 plus epsilon, and lambda 2 plus epsilon, such that they all become distinct. That means lambda 1 plus epsilon and lambda 2 plus epsilon and lambda n plus epsilon, they are all distinct. We can choose epsilon in such a way. That is possible. Okay. So once that is done, we'll get a matrix B epsilon, uh, which has n distinct eigenvalues and along the diagonal. So that will be diagonalizable. Also, B epsilon goes to B. Uh, uh, B epsilon, as epsilon goes to 0, will go to B, which is similar to, this is a typo here, which is similar to A. So thus diagonalizable matrices are dense among all complex, right? And for diagonalizable matrices, you can prove the theorem easily. So one can take the limits and say that one has to justify steps whether this, you can take the limit from outside to inside. And that is because basically the characteristic polynomial consists of polynomials multiplication of, and they are all continuous things. So that can be done. So I think let me try to stop here because I have taken already 6 minutes extra for my class today. So basically what I have tried to do hurriedly today is that you can look at, when you look at linear transformations on vector spaces in Rn under the angle thing, we want linear transformations will preserve angles as well as distances, and that is called isometries. And we try to look at isometries gives rise to what are called orthogonal matrices, and we try to look at when can you say that for a linear transformation which is defined on vector space in Rn, and when can it be made similar to a diagonal matrix. So we looked at isometries in R3, and we saw that the notion of eigenvalues help in decomposing the space into parts and looking at them. So this is the basic sort of philosophy and various forms of matrices. We have just quickly gone through something called the diagonalizability of matrices, and we have shown that matrices are diagonalizable if and only if there is a basis consisting of eigenvectors. That is a necessary and sufficient condition, and for a real symmetric matrices this always happens. Okay, and then gave quickly showed you some illustrations of use of diagonalizability, namely in recognizing quadratic forms, quadratic surfaces. It has applications there, and also one can prove Cayley-Hamilton theorem via diagonalizability and denseness. There are many proofs available for Cayley-Hamilton theorem. I just wanted to quickly expose to you that one should not think of algebra should not have any analysis tools coming in, right? So we brought in denseness and the concept of continuity and limit to say that Cayley-Hamilton theorem can be deduced via diagonalizability. So I think, Dilpreet, are you there?
Yes, sir.
So I think there's time for me to stop.
Yes, please. Yeah, it's fine.
Yeah. So I went slightly fast today. I just wanted to expose the various things. If people have questions, they can ask in the tutorial class, or we will look at the problems, whatever. So up to you. You go ahead.
We can take questions for lecture now.
Yeah, sure.
Okay, so is there any questions, student? Okay, I just, you can unmute yourself now and talk if you want to.
Hello.
Hello? Anyone has any question?
There's no raising hand possible in this, saying that
Uh,
I want to ask.
no,
Yeah,
I
Google,
don't know.
Google Meet has that.
Google Meet do have, yeah.
Yeah, right. No,
Yes.
nobody in chat box. Yeah.
No. People are
Yeah.
thanking you for good proof of Cayley-Hamilton theorem.
Yeah, I have not given the proof actually, but I have given only a path. It is possible. You can try to search the net. I don't think books normally have such proofs included. So you may have to go to the net to find out uh, denseness of diagonalizable matrices in all matrices, and then how does one take limits, kind of a thing. So that is one way, a nice way of proving. If you are an analysis oriented person, then you will like that approach. Okay.
Any other question for sir? I thank you very much, Professor Rana, for presenting these wonderful talks. And sir also thanking you for the same.
Good. Thank you all for
Thank,
listening to me.
thank you. So may I end this session now? So I'm
Yeah.
not going to end this meeting. We will be starting tutorial in 10 minutes.
So
20.
I will join you. Okay.
Okay.
Yeah.
So I posted tutorial sheet to all of you. I hope you got the tutorial sheet. Please let me know.